Welcome everyone to the National Industrial Conference. My name is Santosh Raikar, and today we're going to discuss a critical but often overlooked aspect of plant health, electrical reliability. Our focus will be on the failures that mechanical teams usually notice far too late, and how we can bridge that gap. Let's start with a scenario many of you might recognize. Imagine a large process fan where the bearings keep failing despite repeated mechanical repairs. It's only after a major trip that testing reveals a hidden voltage unbalance and an outdated protection setting. In this case, the plant treated a systemic electrical issue as a series of isolated mechanical failures. The question we must ask is, which electrical evidence should have been part of the very first diagnosis? Why does this perspective matter? From a seasoned practitioner's view, a strong system makes the right action easier under pressure. Electrical failures aren't random. They're preceded by measurable signals like heat, insulation degradation, or power quality shifts. Because these conditions are often hidden behind enclosures, we need a risk-based program that uses engineered inspection and testing to find them before they manifest as mechanical symptoms. By the end of this session, you'll be equipped to build a risk-based electrical asset hierarchy, differentiate between various testing methods, and connect mechanical symptoms to their electrical root causes. Most importantly, we'll discuss how to launch a 90-day pilot program to turn these concepts into immediate field results. Our first step is to see the risk clearly. We need to identify the hidden system conditions that can transform routine maintenance work into a significant enterprise risk. Before we can debate solutions, we need a shared vocabulary. Terms like power quality or protection coordination aren't just technical jargon. They represent specific areas of risk. When we talk about acceptance criteria, we're defining the precise limits that decide whether a piece of equipment is safe to return to service or requires immediate repair. We must remember that the cost of failure is much larger than just the maintenance invoice. Beyond life safety, electrical failures often have a common cause nature. A single failed transformer can halt an entire production line. The complexity of recovery, including long lead times for specialized parts, can impact a company's reputation and cash flow far more than the repair itself. Failures don't happen in a vacuum. They develop through a chain. It starts with stress or contamination, leads to degradation, and eventually shows weak indications like thermal or acoustic signals. If we don't catch it there, it challenges our protection systems, leading to an event. Our goal isn't just to do more testing, but to find the right evidence at the right stage of this chain. The warning signs are almost always there if you know where to look. From thermal cycling in loose connections to the additional stress caused by harmonics and unbalance. These signals are the precursors to disaster. We also need to watch for management drift, such as when severe findings and reports are ignored because of a lack of ownership or outage planning. To assess if your current system is real, ask yourself these 8 questions. Don't answer based on your intentions, but based on evidence. For example, do you have a hierarchical list of assets ranked by consequence? Are your thermography scans performed under documented load? If you can't answer yes with proof, there's a gap in your reliability. In Section 2, we'll look at building the operating model, a disciplined framework with explicit decisions, controls, and evidence. 5 core principles keep this model practical. Safety must always set the method. De-energized work is the default. We choose tests based on the failure mode we're looking for, and we treat protection devices like relays as active reliability systems that need regular maintenance, even if they've never tripped. We call this the Power 6 system. It's a 6-step flow, starting with an inventory of the system, analyzing failure modes, inspecting for visible signs, testing hidden functions, correcting defects, and finally, verifying the results. This loop balances safety, asset health, and production needs. Phase 1 is the inventory. You cannot manage what you haven't mapped. The output here is a critical asset register linked to your single-line diagrams, identifying common cause nodes where a single failure would have a massive impact. Phase 2 is analysis. This is where the electrical reliability team defines the specific failure modes for each asset, whether it's a mechanical mechanism or insulation breakdown, and sets the appropriate inspection intervals based on the level of risk. Phase 3 is inspection. This involves qualified inspectors performing safe visual checks, thermography at known loads, and ultrasound. The key here is context. A temperature reading means nothing if you don't know the load on the circuit at that moment. Phase 4 involves diagnostic testing. This is where we prove the health of hidden components, like cable insulation and breaker functionality. Every test must be measured against defined acceptance criteria to create a traceable record of health. Phase 5 is correction. When defects are found, they must be risk ranked. Maintenance and engineering work together to coordinate safe outages and ensure that repairs, like torquing or cleaning, meet the required standards. The final phase is verification. Before handing the asset back to operations, we verify phase rotation, protection settings, and load stability. We don't just fix it, we confirm that it's ready for the next full operating cycle. To prevent convenience from replacing policy, we use clear decision rules. For instance, if someone proposes energized inspection, the response must be a formal risk assessment and a safe work plan. If a motor has a repeat failure, we mandate an integrated analysis of the entire system, not just a bearing swap. In Section 3, we discuss execution. How do we take this model and make it part of the daily field workflow, management rhythm? Reliability often fails in the gaps between departments. Success requires naming one accountable owner, the electrical authority, while ensuring operations, maintenance, and reliability teams all contribute their expertise to the process. Standard work is what turns intent into execution. By following this 7-step sequence, including a final sustained phase to audit and update our standards, we ensure that the system is repeatable and doesn't depend on a single hero to keep it running. Critical controls must be specific and observable. A control isn't just a manual on a shelf. It's a return to service checklist that someone physically ticks off, or a severity to work workflow that automatically triggers a repair based on a thermal finding. Data collection should be lean. Focus on the minimum data that actually changes a decision. This includes the asset's topology, the test conditions like ambient temperature, raw measurements, and the as-left verification details. Metrics should trigger action, not just admiration. We need leading indicators like the percentage of critical tests completed on time, paired with lagging outcomes like the frequency of protection misoperations or repeat electrical failures. The cadence of review is how culture becomes durable, from quick shift reviews to annual strategy resets. This rhythm ensures that exceptions are escalated and that the standards we've set are actually being followed in the field. Technology should support our discipline, not replace it. Whether it's an EM system linking tasks to results or online condition monitoring for high-consequence assets, these tools should help us correlate data and make better engineering decisions. Finally, we focus on how to apply, verify, and sustain these changes. We want to scale only after we have evidence that the method works. Let's revisit our fan motor case study. Before the intervention, the team was trapped in a cycle of bearing failures every 18 months. They were looking at the symptom, but they missed the signs of phase current imbalance and outdated protection settings. They faced a choice: replace another bearing or investigate the entire system. By applying the Power 6 framework, the intervention shifted from the symptom to the system. They mapped the supply, measured the power quality safely, tested the insulation, and corrected the grounding. Only then did they execute the mechanical bearing work. The success was visible in the evidence. Electrical stress was ruled out, settings were verified against current studies, and mechanical baselines were captured. The lesson is clear. The asset boundary must include its power system, and load context is essential for meaningful data. Let's try a tabletop exercise. If thermography finds a hot main bus joint during peak production, what evidence do you need to establish severity? Who owns the decision to defer or stop production? These are the real-world decisions your team needs to be prepared for. Watch out for common traps. Don't just do calendar-based PMs on every device. Focus on failure modes. Don't take thermal images without recording the load. And never outsource your technical ownership. Your site authority must always make the final risk decisions. You don't have to change everything at once. Start with a 90-day roadmap. Use the first 30 days to baseline a single critical lineup. In the next 30, run the pilot and plan corrections. By day 90, you'll have the KPIs and evidence needed to justify expanding the program. When talking to management, build a business case that balances costs against risk. The value isn't just in the repairs. It's in the avoided outages, the extended life of cables and gear, and the significant reduction in safety risks like arc flash and fire. To maintain the program, use this 12-point field audit. Score only what you can actually observe or trace. If your hierarchy doesn't match the field configuration, or if your protection settings aren't version controlled, you have work to do. As you head back to your plants, remember, electrical reliability becomes visible when you connect condition, protection, and mechanical symptoms. Commit to no tests without criteria, no findings without owners, and no returns without verification. For those who want to dive deeper, I've listed several industry standards and guidance documents here, including NFPA 70B and NETA specifications. These are the foundations of the methods we've discussed today. I'd like to acknowledge the sources of the industrial photography used throughout this deck, which help bring these technical concepts to life. All sources are linked for your reference. I'll leave you with one final question. Which electrical warning will your mechanical team see last? Don't wait for the bearing to fail. Find the hidden electrical condition today. Make the risk visible, make the standard executable, and always verify your results. Thank you.